Hello, friends. Today we are going to be talking about compounds and molecules. We're going to be figuring out how atoms of different elements come together to form other substances. So the first thing we're going to talk about is molecules. So what is a molecule? A molecule is simply a group of atoms bonded together chemically. What a chemical bond is a strong attraction between atoms. They're the way that atoms come together, and they're the way that they're held together. Chemical bonds can only be pulled apart or broken through chemical means. There's no way to physically pull apart a chemical bond. Now, when these groups of atoms come together, bond through chemical bonds, they can be in multiple different formats. They can be two or more atoms of the same element. If we look here, we see down here, this is an example of a molecule made of two atoms of the same element. These little red circles represent oxygen atoms. As you can see, there are two of them, and these lines represent the chemical bond. This is actually what the oxygen that floats through our air looks like. So oxygen doesn't float around us as single atoms of oxygen. It actually floats around as oxygen molecules or O2 molecules, two atoms of oxygen bonded together. The other example of a molecule can be two or more atoms of different elements. So if we look up here, we see many different examples of that. So that means, again, more than one atom coming together and bonding chemically, but in this case, those atoms are of different elements. One very obvious example here is water. You probably already know that water is H2O. If we look up here, we see it's called H2O because it has a single atom of oxygen and two atoms of hydrogen all bonded together. We have a few other examples here. Now we're going to talk about what these are when the molecules include atoms of different elements. They are called compounds, and a molecule is the smallest unit of a compound. So what is a compound? A compound is a pure substance composed of two or more different elements that are joined together by chemical bonds. Now, compounds are made of two or more elements, but always in a specific ratio that is always the same. What do I mean by a specific ratio that is always the same? Or we're going to look at an example to make that make sense. So if we think about water, H2O. A ratio is simply a comparison of the amount of one thing to another. So if we think about water, in order for the compound to be water, there needs to be two hydrogen atoms and one oxygen atom. It must always be a 2-to-1 ratio, or it is no longer water. So that is what we mean when we say they are always made of two or more elements which come together in a specific ratio, which is always the same for that compound. Now, every compound has a very unique set of physical and chemical properties or characteristics, and this is based upon that chemical makeup. So based on the types and number of atoms that are bonded together, the substance has a specific set of properties that is different from all other substances, and again, is based on that chemical makeup. They can only be separated by chemical means. That means I cannot take a water molecule and physically pull it apart. In order for me to separate those chemical bonds, that must happen chemically. And the way that we represent compounds is by a chemical formula. Now, one example that I want to talk about here is this idea of unique properties based on their chemical makeup. So I want to just think about that very obvious example again of water. So if we think about water, H2O, we know, again, that water is made up of two hydrogen atoms bonded to one oxygen atom. Looks like this. Now, water has its own set of properties. It's something that we drink. It's a liquid. It's safe for us to use. It's a universal solvent. It can dissolve lots of different materials based on its polarity. Now, if we were to take that ratio of H2O and change it ever so slightly by just adding another oxygen atom. We barely did anything to it. We're just going to add one more oxygen atom and make it H2O2 instead of H2O. Now we can see that the ratio is no longer the same. It's no longer a 1-to-2 ratio of oxygen to hydrogen. It's now a 1-to-1 ratio, 2 hydrogens to 2 oxygens. Because of this new ratio, this substance or this compound is no longer water. It's now hydrogen peroxide, which we know we wouldn't drink, we wouldn't swim in it. It has many, many different chemical and physical properties than water, simply by adding that one additional oxygen atom to the molecule. So in the universe, there are literally millions and millions and millions of different types of compounds, which we now know are made up of different types of elements chemically bonded together in different ratios. Now, we also know that they all have their own individual set of properties, which are unique from all of the other millions of compounds in the universe. Now, that also tells us that there are millions of different structures of compounds. We have some compounds, like water, which are very small and simple, only 3 atoms with simply 1 oxygen and 2 hydrogens. We have then compounds that increase in size and complexity. So we can also have very, 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 very large molecules with compounds that have lots and lots of different atoms of different elements combined in large shapes and structures. We also have some types of compounds that form themselves in what we call repeating structures. So if we look here, we see things like sugars and a lot of plastics, which if we look here at nylon as an example, or over here we have your regular table sugar, we can see that those compounds have molecular structures that are more complex in shape, but also simply repeat again and again and again. So we have compounds that, again, are very, very small and simple units, and then we have larger and increasing complexity, as well as some compounds that look like repeating patterns. Now we're going to look at how we represent compounds using what is called molecular formulas. So just like in math, you've seen a formula before. Well, to represent a molecule, we also have formulas to do so. We call those molecular formulas, and they are simply a way of representing the chemical compound. In a compound's molecular formula, it tells us a lot of important information that we will need to know about that compound. First, being the elements in the compound. So if we look over here, you've already covered the periodic table. A lot of you probably already can start to see what some of these example compounds are made of. The second thing that it tells us is the number of atoms of each element in the compound. The third thing that it tells us is the number of molecules that are present of that compound. So now we're going to look at how to actually read these molecular formulas in order to gather information about the structure of the compound. So in order to read a molecular formula, there are three components of the formula that you want to be familiar with. The first is the atomic symbol. You already know what those are from our unit on the periodic table. So we know that that is a 1 or 2 letter abbreviation for the element. That's the way it's represented on the periodic table. This simply tells us in the molecular formula the type of elements that are present. So if we look at this as an example, we see that in this particular compound we have carbon, hydrogen, and chlorine represented. Remember, as now we are going to really start practicing reading these, that if it is a single letter symbol, it will be capitalized. If it is a 2-letter symbol, it will be a capitalized first letter and a lowercase second letter. That is how we know that this is chlorine, a single element, not 2 different elements. The second component in all molecular formulas is the subscript. So subscript is the small number that comes after and sort of below the element. This tells us the number of atoms of that element that are present in the molecule. So in order to read this, there's a couple things we want to look at. First, we want to find the subscript. Then we want to determine which atom that subscript belongs to. So again, we know that this comes after the element that it correlates to, not before. So I come to the subscript and I want to look at the preceding symbol to see who that belongs to. In this case, the 3 comes after the H. That tells me that there are 3 hydrogen atoms present in this compound. The third component of a molecular formula is the coefficient. The coefficient is the large number that will come in front of the whole formula. This tells us the number of molecules of that compound that are present. In this case, the coefficient is 4, telling us that in this example, I have 4 molecules of the compound CH3Cl. Hi guys. So the last thing that we're going to do today is find out and practice how to use a chemical formula to count the type and number of atoms that are present. This is going to be very, very important when we enter our unit on chemical reactions. So as we just learned, there are 3 components to the chemical formula. There are the atomic symbols, the coefficients, and the subscripts. So today we're going to find out how to use those 3 components to count the number of atoms of each type of element that are present. So the first thing that you want to do is find out the types of elements that are present. Now, if you look here, I've set up a graphic organizer that could be very helpful in doing this. As you guys practice, you will get better at it. You may not need to do all of this, but as you start, this is a good way to organize your thinking and make sure that you're doing all of the steps in the correct order. So the first thing you want to do is identify what elements are present in the compound. So if we look here, I can see that I have capital C, I have a capital H, and I have a Cl. For some of these, you may recognize them right off the bat, but if not, it's always nice to have your periodic table handy so that you can recognize what that atomic symbol stands for. Capital C, if we look at our periodic table, we know represents carbon. Capital H, again, if I look at my periodic table, I will find that H represents hydrogen. I'm going to write that in. And finally, Cl, if you were to reference your periodic table, you would find represents chlorine. So now that we've identified the elements that are present, we're ready to move on to our next step. So we want to look at the coefficient, if there is one, in front of the formula. So in this case, we see that the large number that comes in front of the molecule is a 4. So I'm going to go ahead and fill in 4 for all of them. Now is a good time to note that there may be an instance where there is no coefficient. So just like in math, if you had a variable with no coefficient in front of it, that would tell you that the coefficient is assumed to be 1. So a good way to remember this is that if there is no coefficient, none means 1. So if you have an example where there is no coefficient in front, you assume that the coefficient is 1. The next thing we want to find out is the subscript in front of all or behind all of our elements. So if we start here, looking at my carbon, the same rule applies for the subscript. If there is none, we can assume that it is 1. So we can see here, there is no written subscript after my carbon, so I can assume that the subscript there is 1. After my hydrogen, I see that there is a 3. That tells me that the subscript for my hydrogen is 3. Finally, I have my chlorine. Very similar to my carbon, I see that there is no written subscript. I know the rule none means 1, so I can assume that subscript is 1. Now, finally, we want to take all of this information and use it to determine how many atoms of each element is present. So what is happening here is this is telling me that I have 4 molecules of the compound CH3Cl. My subscripts tell me that in one of those molecules there's 1 carbon atom, 3 hydrogen atoms, and 1 chlorine atom. If I know that I have 1, 3, and 1
4 times, in order to find out how many atoms are present altogether, I simply need to multiply the number of atoms in one molecule by the number of molecules that are present. This is another reason why setting up this graphic organizer is very helpful. So all you then have to do is take your coefficient, multiply it by your subscript to get the total number of atoms of that element present. So if I take 4 times 1, I know that there are 4 carbon atoms present. Let's go back and check ourselves. In one molecule, there's 1. If I have 4 molecules, that would tell me that I have 4 carbons altogether. The same is true for the next two. I'm going to take my coefficient, which is 4 for hydrogen. I'm going to multiply it by my subscript, which is 3, giving me 12 hydrogen atoms. Finally, let's look at our chlorine. I have a coefficient of 4, a subscript of 1, and a simple multiplication then tells me that I have 4 chlorine atoms present. And you will follow this exact same process anytime you want to determine the number of atoms that are present.